So you should be able to now click on the course evaluation. So at least I think you should, except this isn't, let me publish that. Publish, yeah. So you should be able to take the short survey to that. Of course, it's the same, like if you did the survey last quarter or the quarter before, it's the same thing. I would appreciate all of you doing it so that we can get more feedback as far as teaching, how we're doing, that kind of stuff. So positive and negative, maybe not negative, positive and constructive things to say. So if you have any feedback for me, I'd love to hear it. It is anonymous, so I don't know who said what. Also, it's the last quarter, so right. But please do it. It does matter to us to get all the feedback. My boss definitely reads every single comment that students write and then shares it with me or all of us later. So please do that when you have a chance. Well, let's go ahead and get to business. So today we're mostly going to talk about conditional probability and independence. Before we do that, a few did ask me to go over the quiz you guys just took last week. So let's go ahead and go over the quiz. So here's the quiz setup, right? You have this system of equations, dx dt equals negative x plus 2m, and dm dt is 2 times x over x plus 1 minus m. And we're given that x is the, what is it? Yeah, sorry, I'm looking at this here. Yeah, M and X are the concentrations of mRNA and the concentration of protein. So M is the mRNA and X is the protein. In micro, whatever M's, micro muons, I have no idea what the capital M stands for. It's all right, I don't really care. And T is the time, of course. So we were asked to do a few things with this system of equations and graph. The first question was to properly label the X nullifying and the M nullifying and the steady states. So it's interesting because at least on the quiz that I'm looking at, he tells us what the steady states are. It's all right. So this dashed line, this linear line, has clearly got to be the nullifying that goes with this equation. Because if we solve this for M in terms of X, like set this equal to 0 and solve it, we're definitely going to get a linear thing, right? A straight line. So this dashed line here has to be the M nullifying. And then kind of by elimination, this other curved line or curve, this other curve has to be the X. Sorry, I got that. Used the wrong word. Sorry. The straight line has to be this one, which is the X nullifying. Sorry about that. And this curved one has to be the M nullifying. I don't think you need to do any more work, but right, you could set this equal to 0 and say you get 2m equal to x or m equal to x over 2, which is definitely what this straight line is. And similarly, you could set this equal to 0 and get m equal to 2 times x over x plus 1, which is the other curved one. So that's, oh, and then again, it seems kind of silly that we need to label the steady states when they literally tell us in the quiz what the steady states are. All right, here's a steady state, and here's a steady state. I don't imagine that's the part that anybody's struggling with, right? Because we know how to find steady states. They're just for the equilibriums of different types cross each other. So then we do want to indicate the regions where M and X are increasing / decreasing by drawing arrows that pointing in the directions of the flow. Briefly justify your answers using test points. So I already found one test point. I found the point 3, 1, where X is 3 and Y is and M is 1. If X is 3 and M is 1, we get negative 3 plus 2, which is a negative number. So dx dt, which is the change in X, is going to be negative, meaning we're going to point to the left. And then if you plug in 3, 1 for, again, X and M, you get 2 times 3 over 4 minus 1. 2 times 3/4 is 1.5, minus 1 is 0.5. So we're definitely going up and left, right? Left because this was negative, up because this was positive. So I like to draw the arrows like this, where you have one up, one left, but you could also draw the arrow like pointing up and to the left. And then I think you only need to use one test point, because then you can say whenever you cross a null line, you're going to change the direction of the thing that's not zero, right? So, or that is zero, sorry. So like down here, we're pointing up and left. On this M null line, where dm dt is zero, where the change in M is zero, you're going to be purely horizontal, right? There is no vertical change because dm dt is zero. So when I go to the other side here, now I have to be pointing downwards, right? Here dm dt is positive, here dm dt is zero, here dm dt is change sign and is negative. But we're still pointing to the left. And then up in here, when I cross this x null line, well, I'm changing from going left to going right. It's still down. And that's going to be the truth everywhere over here. Right, until I cross another null line. So when I cross this null line here, well, again, this is an M null line where everything is purely horizontal, so my vertical things is going to change from being down to being up. But still to the right. Up, still to the right. And then I guess we could look down, over here as well. So crossing this null line, the x null line, where everything is vertical because there's no change in x, right? Here we're pointing right, then we're not pointing right or left, we're just pointing down. And then down here, we're going to change to pointing left. And still down. That would be the case. Just in this little sliver right here. And then when we cross this one, we're going to change from pointing left to pointing right. So here we're right and down, right and down. Why do I feel like I'm making a mistake here? It's easy to make mistakes if you're not careful. Let me be a little extra careful here. So, oh yeah, sorry, I messed up on the last one. Right, here we're left, here we're down and left. And again, this is an M null time where everything's horizontal, right? So we change from down to being up. Sorry about that. So over here we are still left and up. Up. Same up here. This is not a null line. This is just the axis. Right, we're in the same region as our original test point, so it should be the same. Okay. Any questions about that before we move to the next part? Let's see. The next one says, for the initial conditions x equals 2 and m equals 0, sketch the trajectory x of t, y of t in the phase plane. So we're starting at 2, 0, right here. And we know we have to be going up and to the left, that one. We also know that this is because they told us that this steady state is a stable node, and that this steady state is a Saturn. So here's what we're going to do. We're going to go up and to the left, and this null line, which is an x null line, every part on that null line is purely vertical. So we're going to cross this in a purely vertical way. And in fact, let me draw that. So I know that on this null line here, everything is just straight up. There is no left or right. But then on this null line here, everything is straight right. So what's going to happen is we're going to go up and to the left. We're going to cross this purely vertically. And then from here, we have to go up and to the right. And now the thing is, I can't really cross this curvy null line because I have to cross it in a purely horizontal way. And there's no way to get up to it while being purely horizontal. So I just kind of get forced up and to the right, 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 up and to the right to my equilibrium. So that's looking like my trajectory. It's not too terrible. And then part D, they ask us to sketch x versus time and m versus time. corresponding to the trajectory that you plotted in the phase plane right here. So let's do the x one first. So x starts at 2, gets smaller for a bit, maybe as small as 1. Again, we're going to be kind of guesstimating here. So it's the smallest 1, and then it kind of gets back up and gets as big as 3. So it gets closer and closer and closer to 3. So I would say 3 is going to be kind of asymptotic. We're going to start at 2. We're going to decrease kind of like that. That's not the best I've ever done. It does not. So right, we're gonna decrease. We're gonna kind of bottom out at 1, and then we're gonna increase and get closer and closer and closer to 3. Again, right, this isn't perfect, but it's all right. On the other hand, the y values are just going to get larger and larger and larger and larger and larger and larger and larger until they get closer and closer to 1.5. Sorry, not the y values, the m values. So the m values start at 0, and then they're just going to get asymptotically close to 1.5. Maybe like that. And then the last question, what is the concentration of protein X in the long run? Well, X is getting closer and closer and closer to 3, and X is representing the concentration of protein. So X would be 3, whatever the units are there, micro, I don't know what the capital M is supposed to stand for. The second part of this question is a little bit harder. What is the rate of the production of protein X in the long run, i.e. as time goes to infinity? So I'm asking what dx dt is going to. Well, I know that X is going to 3 and that M is going to 1.5. And if I plug in 3 and 1.5, well, oh yeah, I'm going to get 0, right? So if I plug in -3 plus 2 times 1.5, I get negative equals to 0. If you're ending up going towards the steady state, which is, I should say, a stable equilibrium, right? If you end up going towards a stable equilibrium, you should be getting to a place where dx dt is 0 and dy dt is 0. So dx dt is going to 0 micro whatever is per minute as t goes to infinity. So that's how that quiz should have mostly gone. Yeah, I don't know if he's supposed to, I imagine he hasn't posted solutions yet. Maybe he has, I don't know, but that's the quiz. Hopefully it went all right. Yeah. All right, so changing gears. I imagine, actually, question statement for you guys. I imagine he hasn't talked much yet about the format, or really more, I guess, the content of your final exam. Like I'm imagining it's probably cumulative, but I also imagine it might be focused more on what we were doing right now because you haven't been tested on it. So if you know, or if he said, I mean, I've been in class in those days, so I haven't seen him say anything in class about it. But if you guys hear something, let me know so I can kind of prepare accordingly to help you prepare for your final. All right, let's go ahead and look at some conditional probability stuff, which also has to do with independence. And I'm going to do an example we did in class because it's kind of a good starting place for things. I guess I can use a different suit. So let's say we draw 2 cards from a deck, from a standard deck, right? 52 cards, 4 of each rank, 13 of each suit, without replacement. What's the probability that the first and second card are diamonds? Are both diamonds. Okay, so let's say that A is the event where the first card is a diamond, and B is the event where the second card is a diamond. Also, I thought, by the way, if you didn't go to class today, I do think his PowerPoint with the stars and the circles and the blue and the red was a really good visual of how this conditional probability stuff works. So if you haven't watched it, I encourage all of you to watch it. I think it was well done and made it kind of easy to understand what's happening. So if I'm trying to find the probability that the first card is a diamond and the second card is a diamond, that's like an intersection, right? I want to know the probability that A and B happen. All right. Well, the chance of the first card being a diamond is 13 chances out of, or 13 diamonds out of 52 cards. And then since we're doing this without replacement, there's only 51 cards left and only 12 of them are diamonds. So the next probability is 12 out of 51. And also, a quick aside here. I noticed in class today that someone asked a good question, which he kind of ignored, which is fine. I understand ignoring it because it's not an easy question to answer. He asked, someone asked, like, how do you know when you multiply versus when you add? And there's really no good hard and fast rules about this. It's kind of very dependent on the situation. But one rule that kind of, or one guiding technique that works a lot is if you want a thing and another thing to happen, that usually means you're multiplying the probabilities together. You're saying, I want to know what's the chances of this happening and this happening, and if they're essentially, well, I don't want to say independent here, but right, if you know what that is, you know what that is, you want all of the kind of possibilities. So there's 13 ways of this happening, there's 12 ways of this happening, multiply them together, you get 13 times 12 is 156 out of whatever that bottom number is. And then kind of to contrast that, if you want something to happen or another thing to happen, we often add those things together. And it's especially kind of evident when you're talking about an intersection versus a union, right? When you have an intersection of two things, you want both A and B to happen, and we multiply those probabilities together. When you have a union of things you want to happen, A or B, you typically add the probability of A and the probability of B, and you subtract off the intersection. So that's kind of again, not a strictly works every single time rule, but it's definitely a helpful way of thinking about things. If you want one thing and another thing to happen, we typically multiply. If you want one thing or another thing to happen, we typically add. So that's something you can use, right? And typically means multiply, or typically means add. For this one, I don't really care what the numbers are. We can reduce this though, right? 13 over 52 is 1/4, and 12 over 4 gives you a 3, so you get 3 over 51, which is 1/17. But more the important point here is that this is actually equal to the probability of A, right? So 13 out of 52, right? The probability of the first card is a diamond, 13 out of 52. The second probability, 12 out of 51, is actually a conditional probability. It's the probability that B happens given that A has already happened. So that's what we're doing there. We're saying, well, right, if you just asked what the probability of the second card is a diamond, you didn't know anything about the first card, it actually wouldn't be 12 out of 51. It'd be a different probability. But since we know the first card was a diamond, this second probability, this conditional probability, is 12 out of 51. On the other hand, and I know you talked about this too, if we do have replacement, so if we replace the first card, then the probability of A and B is going to be just 13 out of 52 times 13 out of 52. Right? There's 13 diamonds out of 52 cards. There's a 1/4 chance of getting it. And then you put the card back in and you pull out another card. There's again a 1/4 chance of getting a diamond. So here, that's a 1/4 times a 1/4, which is 1/16. A slightly higher probability, by the way, which again isn't surprising, right? If you put the card back, there's going to be a higher chance of getting both of them being diamonds. So we have some formulas that I want to talk about. They're not terrible. They are these conditional probability formulas. And so I kind of think of them as that the probability of A and B happening A intersect B, right? We often read an intersect as an and. Is the probability that A happens times the probability that B happens given A has already happened. And again, I write it this way if I'm kind of like some situations more than others, you kind of think of one event possibly happening before the other event. In this, writing this way, I'm definitely thinking that A would be happening before B. I'm saying it's the probability that B given A has happened times the probability that A has happened. But we can also write it as the probability that B has happened given or times the probability of A happening given that B has already happened. So both these formulas are valid formulas for an intersection. And then they both lead to, if we divide, right, if we divide the probability of A intersect B by either the probability of B or the probability of A, we get the following formulas for conditional probability. The probability of B given A is the probability of B and A happening divided by the probability that A happens. Or the probability of A given B is the probability of A and B happening divided by the probability of B. Let's look at some examples. Again, with these decks of cards. So let's look at this next one. And there's kind of, and he definitely talked about this in class, there's kind of two ways you can think about calculating this probability. You can either, well, let's just do the example and then we'll say the words. So let's say one card is drawn from the 52 card deck. One card is drawn. And we want to know what's the probability that it's a queen given that it's a face card. The probability it is a queen given we know it's a face card. Okay, so there are two ways of doing this. One way is kind of just to look at what he was talking about is the reduced sample space. So our reduced sample space here, well, how many face cards are in the deck? Anybody, how many face cards? This is something you all need to be able to answer, for sure. I could imagine there being a question like this on your test. There's 4 queens. There's also 4 jacks. And there's also 4 kings. So there's 4 of each face card. How many? So again, and the face cards are jacks, queens, and kings. So there's going to be 12 total face cards. Right? We have the 4 jacks, the 4 queens, and the 4 kings. All right. So what's the probability? Well, I should blah, blah, blah. I should say our total sample space is 12. So the probability of a queen, I guess so right, you're supposed to label things. I'm doing a poor job of that. So let's say it being a queen is A, the event A, and it being a face card is the event B. So the probability of A given B is, well, there's 4 ways of being a queen in a face card divided by the 12 ways of being a face card, which is 1/3. Basically taking all the things you want out of your reduced sample space. Alternatively, it's going to feel very much the same, but it's slightly different. The other way we can calculate is we can use the formula. We can say, oh, the probability of A given B is the probability of A intersect B divided by the probability of B. The probability of A intersect B, right? That's the probability of being a queen and a face card. So there's 4 queens that are face cards. Every queen's a face card, right? So the probability of being a queen and a face card is 4 out of 52. The probability of being a face card is 12 out of 52. the 52s cancel, and you get 4 12ths, which is 1/3. So typically, I think it's kind of nicer to think about the reduced sample space and kind of see what we're doing. But sometimes that's not really an option. Sometimes we're kind of just given the probabilities and we have to find the conditional probability. So when you're given probabilities, it makes more sense to be like, oh yeah, it's the probability of the intersection divided by the probability of kind of a larger space. Graphically, the idea is that if you've got some sample space, omega, and some A and some B, we're basically taking, well, if I want to know the probability of A given B, that means we are living in B, right? This is our reduced sample space. And we're asking, what's the probability that you're in A given that you're B? Well, that's the probability that you're in here, right? Because that's the only part of A we get to have. And that's exactly the probability of A intersect B divided by the probability. So there's a graphical representation of it as well. Hopefully that helps you see it a little bit better. Let's look at more cards. So what's the probability of drawing a heart? That's going to be our A, given that it is a 7. Okay, well, that's our B. Our reduced sample space, I'm going to call omega B. Our reduced sample space, well, we're giving it to 7, so it's either a 7 of hearts, a 7 of diamonds, a 7 of clubs, which I'm terrible drawing the clubs, or a 7, some people call them clovers, 7 clovers, 7 clovers, or a 7 of spades. I'm also not great at drawing. Okay, so there's our sample space. There's 4 things in it. How many of them are hearts? Oh, 1 of them. So the probability of A given B is going to be the one thing that's what we want, right? There is 1 heart in our reduced sample space out of 4 total possibilities. Or we could say it's the probability of A given B, right? It's the probability of A intersect B divided by the probability of B. A intersect B is that, well, A is that you're a heart, B is that you're a 7. There's only 1 7 of hearts. So the probability of getting a 7 of hearts is 1 in 52. Divided by the probability of getting a 7, which is 4 out of 52, which is 1/4. So basically the difference is just like this way you're just kind of thinking it out. This way you're saying, I know the probabilities. You're basically just taking these same numbers and dividing them each by the total number of things in your sample space, in your entire sample space. Let me do one more before I pause for a second. So let's say I want to know the probability of a king given that it's a club. Okay. Well, probably going to be a king given that it's a club is going to be, let's see. There's how many clubs? So our reduced sample space is all the clubs, right? So the given thing is always your reduced sample space. It's the new space you're living in. Our new sample space is the space of clubs. We're at the club. No, we're at the club. We're in the club lane. So there are 13 clubs. So that's going to be the divisor. And then of those 13 clubs, how many of them are kings? Uno, 1. Other words for one, in French. I don't know how to say 1 in a lot of languages, so I feel like I should. So yeah, 1/13, I can't reduce that. You could also have written it as the probability of A to intersect B divided by the probability of B. The probability of being a king and a club is, again, 1 in 52. Probability of being a club is 13 and 52. Same thing, 113. That is a 13. My 13s often look like the letter B because I kind of stick my 1 and my 3 too close to each other. So before we continue on, let me ask you this. Any questions so far? Anything you'd like me to clarify or talk about more? Okay. So, do a few more examples. A family. So this is where things get kind of interesting. So, family has 2 children. One is a girl. That's the given information. Right, so we are given one is a girl. Sure, yeah. And I want to know what's the probability that both are girls. So if you weren't being careful, you might think the answer is 1/2. Because you're like, oh, well, one of them's a girl. That means, and the other one, right? Assuming, right, the 50-50 chance of being a boy or a girl. That means the other one, there's 50% chance of being a girl. But that's not the case here because we already have some information. So let's write it out this way. What is our reduced sample space? Well, you can either have, if you have, we know one child's a girl, it could either be the first child was a girl and the second was a boy, or the first child was a boy and the second was a girl, or the first child was a girl and the second child was a girl. So we want the probability of A given B. Well, the only way we get both girls is this one way out of the 3 possibilities in our reduced sample space. So if you know one kid's a girl, there's a 1/3 chance that the other kid's a girl. Kind of interesting. Kind of right. You're kind of like, someone said they had 2 kids, you saw one of them was a girl, you'd be like, oh, well, then yeah, there's a 50% chance. There's actually a 1/3 chance that it was a girl. Probability strikes again. We could also have done this the other way, right? We could have said it's the probability of having 2 girls and one is a girl. Well, there's only one way to have 2 girls. It's a girl. Out of 4 possibilities, because there are 4 ways you can have 2 kids: boy, boy, girl, boy, girl, boy. Divided by the 3 out of 4 ways, right? Boy is not in there. But there are 3 out of 4 ways to have a girl. No, or 3 ways that at least one's a girl. So yeah, 1/3. Let's contrast that with, I've reframed that. So same question, except now we know 2 children, and we know the oldest is a girl. What's the probability of 2 girls? Well, now there's only 2 possibilities in our sample space. First kid's a girl, second kid's a girl, or first kid's a girl, second kid's a boy. Right? There aren't any other options because we know that the oldest child is a girl. So the probability of, again, 2 girls being A and having 2 children being, knowing the oldest is a girl being B, the probability of A given B, well, there's one way to have 2 girls out of 2 ways to have the oldest child being a girl. There's a 50% chance. Which again would be the same as if we did the probability of having 2 girls, which is 1/4 out of the probability of having the oldest being a girl, which is 1/2. Yeah. Now, something interesting to say here. For this problem we just did, I want to point out that knowing that the first child was a girl didn't affect the probability of the second child was a girl. Right? So here in this problem, the probability of A given B, and probably having 2 girls, given that the oldest is a girl, is the same as I feel like I'm saying this kind of wrong. Oh, I should have written it slightly differently. What's the probability? I guess you could phrase the question in a better way. What's the probability if the oldest is a girl? What's the probability of the youngest being a girl? It's still asking the same question, just in a better way. Sorry. So the probability that the youngest is a girl, given the oldest is a girl, is the same as the probability that the youngest is a girl. This is 1/2. This is 1/2. So what we would say here is that B's occurrence has no effect on whether or not, or I should say on the probability of A. This is the definition of independence. So in this particular problem, we would say that A and B are independent. Knowing that B happened didn't affect the probability of A. Yeah. There are many ways to write this. There are many formulaic ways to write this. So this is probably the way I like to think of it the best. Right? If you know B has happened, probability of A given B didn't change the probability of A, right? So equal the probability of A. So there are 3 different ways you could write things are independent. So here's what we have so far. We back it up a little bit. Here's our formulas for A intersect B, where the probability of A intersect B is equal to the probability of A times the probability of B. And then we can also solve for this and say that the probability of B given A is equal to the probability of A intersect B divided by the probability of A. Well, if A and B are independent, right? And here's what we can say. The probability of B given A is equal to the probability of B. But if we use that in this formula here, that means this is going to get replaced. So we could also write it as the probability of A, intersect B is equal to the probability of A times the probability of B. So if events are independent, the probability of A and B is the probability of A times the probability of B. Great. I feel like there's a third one I'm missing here. These are kind of the main ones. Yeah, and again, you could also write it as the probability of A given B is the probability of A. So, independence. Knowing a thing has happened doesn't change the probability of the other thing happening. probability that A has happened given that B has happened is the same as the probability that just A has happened. Yeah. All right. So I feel like I had something else important to say. I don't want to say. So I want to just make sure that everyone's super cool with the fact that independence and mutual exclusivity are totally kind of unrelated. Or they don't mean the same thing. I've seen a lot of students over the years confuse being mutually exclusive or disjoint with being independent, but they're not the same at all. In fact, if you know things are disjoint, you know they are not independent. So let's say that A and B were disjoint. So A intersect B is the empty set. I'm sorry, there's no zero in there. So I can take nothing. Or if you prefer, you can use the Greek letter phi. So if I want to know the probability of A given B, well, right, if A and B have a zero intersection, probably A given B is going to be zero. You could also just say, well, it's the probability of A intersect B divided by the probability of B. But A intersect B, there isn't any probability that happens, so it's going to be zero. So if things are disjoint, the conditional probability is going to be zero. And that's almost always going to be different than, right? This is not going to equal the probability of A. So if things are disjoint, they are never independent, because knowing that one happens affects the probability that the other one happens, right? If you know that B has happened, you know that A cannot have happened. That means they're not independent, because knowing something about one of them tells you something about the other one. All right. Let's look at another example. So it can be hard to kind of intuitively know when things are independent. Right, like so for example, for decks of cards, if we draw with replacement, we're gonna keep putting the card back in after we've drawn it. Usually those events are independent because one of them happening doesn't affect the probability that the next thing happens. Yeah, let's look at this example. A multiple choice test has 5 possible answers. A, B, C, D, and we want to know what's the probability of guessing all of them correct. There's 10 questions. Okay. Okay, so these events, and again, we're assuming, right, if we're really guessing, or we've done any information about any of the questions, we're assuming that each event is independent, right? Guessing on one question doesn't change the probability of your guess in the next question. So the probability of getting all 10 right is going to be the probability that the first one's correct times the probability that the second one's correct, all the way to times the probability that the last one's correct. And again, the reason we're adding here, let's just look at the first two actually. Oh, sorry, the reason we're multiplying here. Let's look at the first two. So in the first two, right, there's A, B, C, D, and E. There's A, B, C, D, and E. There's a 1/5 chance we get this one right by guessing. There's a 1/5 chance we get this one right by guessing. And there's a 1/25 chance we get both of them right by guessing, because the 5 possibilities here have to multiply by the 5 possibilities here, right? There are literally 25 different ways you could guess. You could guess AA, AB, AC, AD, AE. That's 5 possibilities. But then you can guess BA, BB, BC, BD, BE, and then CA, CB, CC, CB, CD, and then DA, DB, DC, DD, DE, and then EA, EB, EC, ED, EE. There are literally 25 ways you can guess the first 2 questions. And of those 25 ways you can guess the first 2, only one of them is where both of them are correct. Right? There's only one combination of these 2 things that are both right. So there's a 1/5 chance of getting that one right times a 1/5 chance of getting that one. That's why we're multiplying. We want something to happen and another thing to happen. Because when you want the and to happen, there's a multiplicative effect on how many possible things can happen. And then we just keep multiplying by 1/5 all the way to the very end. So we end up getting a 1 in 5 to the 10th chance, which I feel like I forgot something. Oh, no, I didn't. Which is very small. It's about 0.0000001024. So a lot, 6 zeros, 1024. 1/10, 100,000. Like a 1 in 10 million chance of guessing all 10 questions correct. Okay. Yeah, we got time. We got 2 minutes. We got 2 minutes. Okay, so second part here. And I know you did one like this in class, but let's see. What's the probability of getting 9 correct? Okay. So probability of 9 correct would be, I don't know why I'm writing this again. I feel like I'm looking at the notes. I'm like, this is not how I would do it. So one way you could do it, I think you have to do it this way. Yeah. So you get the first one correct. Sorry. First one wrong. Yeah. And the other 9 correct. Or you get the second one wrong. 9 and the other 9 correct. Notice I said or. So you get the first one wrong and the other 9 correct. Or, meaning plus, the second one wrong and the other 9 correct, plus all the way down to the last one wrong and the other 9 correct. Okay, let's figure this out real quick. This is something that comes up. I know we're out of time. So what's probably getting the first one wrong? It's going to be 4 out of 5. What's probably getting the other 9 correct? It's going to be 1/5 to the 9th power. Right? Instead of getting all 10 correct, 1/5 to the 10, it's 9 correct, 1 wrong. But then that's going to be the same. Right? That probability is also going to be 4/5 times 1/5 to the 9th. All the way down to the last one, which is going to be 4/5 times 1/5 to the 9th. So the probability of getting any 9 correct and 1 wrong, right? So getting exactly 9 correct is going to be, well, there's 10 ways of doing it. 10 choose 1 out of the 10 questions, you're choosing 1 to be wrong. And then there's a 4/5 probability of that 1 being wrong. And then there's a 1/5 to the 9th probability of getting the other 9 right. That's how you would calculate the probability of getting exactly 9 right and exactly 1 wrong.